welcome to Easy BTech channel. So the major aim of this channel is to make BTech easier to the students, right? In the last lecture, we have seen what is binary number system and what is decimal number system. So in this lecture, we will see how to convert the given binary number to decimal number, and decimal number, if the decimal number is given, how to find the corresponding binary equivalent. So those two things we will see in this lecture, right? So how to, if a binary number is given to us, a binary number is given to us, and how to find the corresponding decimal equivalent for this. How to find the corresponding decimal equivalent for that number. So for example, if the given binary number is is having n integer bits and m fractional bits. So what we have to do means, so we have to assign positive weights to the integer part and negative weights for the fractional part. For example, to this 2 power 0, 2 power 1 and so on, 2 power n minus 2, 2 power n minus 1, and similarly for this 2 power minus 1, 2 power minus 2 and 2 power minus m. So then we have to multiply each bit value with the corresponding weight. We have to multiply each bit value, as it is a binary number, it will have either 0 or 1. So if 1 is present, we have to multiply with that respective weight, and then we have to sum all those values. So that means how it will, the corresponding decimal equivalent. So if this is the binary number, so we have to multiply 2 power n minus 1 into bn minus 1 plus 2 power n minus 2 into bn minus 2 and so on, plus 2 power 1 into b1 plus 2 power 0 into b0. So these are the weights correspond, this is the expression corresponding to integer part. For fractional part, we will have negative weights. So 2 power minus 1 into b minus 1 plus 2 power minus 2 into b minus 2 and plus on so on, plus 2 power minus m into b minus m. So we have to multiply the corresponding bit value with the corresponding weight, and then we have to sum all those values. We will get the corresponding decimal equivalent of the given binary number. So the same thing we can express in the summation in the shorthand notation in this way. So I running from minus m. So this corresponds to fractional part up to n minus 1. So this corresponds to integer part, whereas the lower limit corresponds to fractional part, and then ba into 2 power I. So ba is the corresponding value. So ba will be either 0 or 1, right? So we'll see with the help of an example this. So these two powers will be useful while converting or while finding the decimal equivalent for the given binary number. So 2 power 0 means 1, 2 power 1 means 2, 2 power 2 means 4, 2 power 3 means 8, 2 power 4 means 16, 2 power 5 means 32, 2 power 6 means 64, 2 power 7 means 128, and 2 power 8 means 256. Similarly, 2 power minus 1 means 0.5, 2 power minus 2 means 0.25, 2 power minus 3 means 0.125, 2 power minus 4 means 0.0625, and 2 power minus 5 means 0.03125. So these will be useful for finding the decimal equivalent of a given binary number. So we'll see with the help of example. So let us look at this example. For example, the given binary number is 101011. So this is the given binary number to us. We have to find the corresponding decimal equivalent for this. So what we have to do? first we have to assign the weights 2 power 0. So this is the LSB. So LSB will have least weight. So whereas this is MSB, MSB will have highest weight. So we have to start assigning the weights in the increasing order from LSB to MSB. So this will have a weight of 2 power 1. This will have a weight of 2 power 2. This will have a weight of 2 power 3. This will have a weight of 2 power 4. And this will have a weight of 2 power 5. Now the second step is we have to multiply the positional weight with the respect to bit value. So how then sum all those values. So this will be 1 into 2 power 5 plus 0 into 2 power 4 plus 1 into 2 power 3 plus 0 into 2 power 2 plus 1 into 2 power 1 plus 1 into 2 power 0. So what is 2 power 5? So 2 power 5 is 32. 1 into 2 power 5 is 32 plus 0 into 2 power 4. Anyway, it will be 0. So plus 1 into 2 power 3 means 8. So again 0 into 2 power 2 means 0. So plus 1 into 2 power 1 means 2. Plus 1 into 2 power 0 means 2 power 0 means 1. So 1 into 1 is 1. So what is the corresponding value? 32 plus 8, 40, 40 plus 2, 42, 42 plus 1, 43. So for the given binary number, the corresponding decimal equivalent is 43 to the base 10. So for the given binary number 101011, the corresponding decimal equivalent is 43. Right? Is it clear? So what we have to do? We have to assign the weights in the order of 2 power and assigning the weights from LSB to MSB. Then we have to multiply with the respective bit value and sum all those values. We will get the corresponding decimal equivalent for the given binary number. Right? Next. Second example. So second example, in this example we are considering the fractional binary number, and we will find the corresponding decimal equivalent for this. So if we are having fractional part, then we have to assign weights in the negative powers. So this will have weight of 2 power minus 1, 2 power minus 2, 2 power minus 3 and 2 power minus 4. So after assigning the weights, we have to multiply with the respective bit value. So 0 into 2 power minus 1 plus 1 into 2 power minus 2 plus 0 into 2 power minus 3 plus 1 into 2 power minus 4. So this will be 0. So 1 into 2 power minus 2 means it will be 0.25, and 1 into 2 power minus 3 means it will be 0, whereas this will be 0.0625. 0.0625. So we'll have only 0.25 plus 0.0625. So if we add these two, we will get 0.3125. So this is the decimal equivalent for the given binary number 0101. So what we have to do while converting a given fractional binary number to find the decimal equivalent, so we have to assign the weights in the negative order. From the fractional point we have to assign the weights in the increasing order, so till LSB 2 power minus 1, 2 power minus 2, 2 power minus 3 and 2 power minus 4, and multiply with the respective bit value and sum all those, we will get the corresponding decimal equivalent for the given binary number. Now we will look at one more example which is having both integer part as well as fractional part. We'll find the corresponding decimal equivalent for this binary number. So what we have to do, from the fractional point, we have to assign for integer part the weights increasing order to power 0, to power 1 and to power 2, whereas for the fractional part we have to assign negative weights to power minus 1 to power minus 2. Now the second step is multiply the respective weights with the respective bit value. So 1 into 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0. So this is for the integer part. For fractional part, we have to multiply with respect to negative weight. So 1 into 2 power minus 1 plus 1 into 2 power minus 2. Now 1 into 2 power 2 means 4. So this will be 0. So plus 1 into 2 power 0 means 1. So this will be 1. So 1 into 2 power minus 1 means 0.5. 0.5. So 1 into 2 power minus 2 means 0.25. So 4 plus 5, integer part is giving 5, whereas fractional part is giving zero point 0.5 plus 0.25, that means 0.75. Now if we add both, we will get 5.75. So this is the decimal equivalent for the given binary number 101.11. For that, the answer at the decimal equivalent is 5.75. So we have to assign positive weights for the integer part and negative weights for the fractional part. Multiply the weights with respect to bits and sum all those values. We will get the corresponding decimal equivalent for the given binary number. Right? Is it clear for everyone? Now we'll see one more example. One more example so you can understand betterly. So what we have to do, first step is assign weights for the integer part with the positive weights, for fractional parts negative weight, multiply with the respective bit value, sum all those values. You will get the decimal equivalent for the given binary number. So this will have 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, and this will have 2 power minus 1 and 2 power minus 2. Now multiply with respect to bit value. So 1 into 2 power 4 plus 1 into 2 power 3 plus 0 into 2 power 2 plus 1 into 2 power 1 plus 0 into 2 power 0. So this is for integer part. For fractional part, 1 into 2 power minus 1 plus 1 into 2 power minus 2. Now find the corresponding values. So 2 power 4 means 60, 2 power 3 means 8 plus 0 plus 1 into 2 power 2 power 1 means 2 plus 0 plus 1 into 2 power minus 1 means 0.5 plus 1 into 2 power minus 2 means 0.25. So 16 plus 8, 24. 24 plus 2, 26. So integer part is giving 26, whereas fractional point 0.5 plus 0.25 is 0.75. So the corresponding decimal equivalent for the given binary number is 26.75. 26.75. Is it clear? We will see one more example, or you can try these exercise problems on your own and comment in the comment section. Try to give your answers or enter your answers in the comment section. We will provide you the answers. You can cross check your answers, right? So next we will see about how to convert the given decimal number or how to find the binary equivalent for the given decimal number. So for this we have to consider the integer part separately and the fractional part separately. So for the integer part, what we have to do means repeatedly divide the given decimal number by 2. What we have to do? Repeatedly divide the given decimal number by 2 and continue accumulating the reminders until the integer coefficient becomes 0. So what basically we have to do for the integer part means we have to repeatedly divide the given number by 2, and then what we have to do, arrange the reminders in the reverse order. So whatever reminders we will get, so those reminders we have to write in the reverse order. That means from bottom to top. So this is about integer part, whereas about fractional part, coming to fractional part, it is just opposite to what we are doing for the integer part we are dividing the given decimal number, whereas for fractional part we have to multiply the given fraction by 2, multiply the given fraction by 2 and accumulate the integer part. So if you multiply the fractional part, we will get integer part as well as fractional part. So here we have to collect the integer part whatever we will get by multiplying the given fractional part with 2. So this process we have to continue until the fractional part becomes 0. So whenever the fractional part becomes 0, then we will not get any integer part. So the process will stop when the fractional part becomes 0. So for this, the important point is the integer parts, whatever we are getting, we have to write in the same order they are obtained. So this is the difference between, so there are two differences. For integer part, we have to divide the given number, whatever reminders we are getting, so those we have to write in the reverse order. Whereas for fractional part, we have to multiply the given fraction repeatedly by 2, and we have to collect the accumulate the integer in the same order. So these are the two procedures that we have to follow for integer part as well as fractional part. So this will be more clear if you see with the help of an example, right? So the given decimal number is 64. We have to find the corresponding binary equivalent for this number. So this is having only the integer part. So we have to divide the given number 64 repeatedly with 2. So 64 if we divide with 2 32 times it will divide, and the remainder is 0. Again we have to divide with 2. It divides 32 by 16 times, so the remainder is 0. Again we have to divide with 2, so it divides 16 by 8 times and the remainder is 0. Again we have to divide the 8 with 2. It divides by 4 times, the remainder is 0. Again we have to divide with 2, and it divides 4 by 2 times and the remainder is 0. Again we have to divide with 2, so it divides by 1 time and the remainder is 0. So the further division is not possible. So what we have to do means, so we have to, whatever reminders we got, we have to write in the reverse order or from bottom to top. So the corresponding binary equivalent for the given decimal number 64 is 1 followed by how many zeros? 1 2 3 4 5 6, 6 zeros. 1 2 3 4 5 6. So this is the binary equivalent for the given decimal number 64, right? So what we have done, we have repeatedly divided the given decimal number with 2 till the division is not possible, and we have written the reminders in the reverse order. reverse order, right? Is it clear? And next we will see one more example. The given decimal number is 239. 239. So divide 239 with 2. 2 ones are 2. 2 ones are 2. And then 19 means 2 9 times. And the remainder will be 1. 2 1 ones are 1119 is 238. The remainder is 1. So again, if we divide with 2, how many times it will divide? 2 5s are 10 and 19 we will have. Again, if we divide with the 9, 18. So the remainder will be 1. Now again, if we divide with 2, 2 twos are 4 and again we will have 19. Again 2 19 and 2 nines are 18. So the remainder will be 1. Again if we divide with 2, 2 14s are 28. So we'll have remainder 1. Again if we divide with 2, 2 sevens are 14. Remainder is 0. Again if we divide with 2, 2 threes are 6. Remainder is 1. Again if we divide with 2, 2 ones are 2 and the remainder is 1. Now further division is not possible. Now write the whatever reminders we got in the reverse order. So corresponding binary equivalent for the given decimal number is 1 1 1 1 1 1 0 0 and then 1 1 1 4 ones 1 1 1 1. So this is the binary equivalent for the given decimal number 239. So 1 1 1 0 1 1 1 1 is the binary equivalent for the given decimal number 239. Right? Now we will see how to find the binary equivalent for the given decimal number which is having only fractional part. So what we have said, if it is fractional part we have to multiply by 2. So 0.75 if you multiply with 2, so you will get 2 5s are 10, 2 7s are 14, 5. So 1.50. So then whatever fractional part we will get, so that fractional part we have to take and again we have to multiply with 2. So if you multiply with 2 we will get 1.0. So again if you take the fractional part and if you multiply you will get 0. You will get 0. So for the fractional part what we have said, we have to accumulate the integers. We have to accumulate the integers in the same order. So we got two integer parts, those are 1 1. So that is why for the given decimal number, the corresponding binary equivalent is 0.11. 0.11. So this is the binary equivalent for the given decimal number 0.75. So what we have to do? We have to repeatedly multiply the fractional part. So we have to start accumulating the integer part whatever we will get in the same order. So this is the important point we have to remember. For integer part, if the decimal number is having integer part, while finding the corresponding binary equivalent we have to accumulate the reminders in the reverse order. So for a fractional part we have to write the reminders or we have to collect the integer part. We have to collect the integer part in the same order. So this we have to remember. So if you write in the reverse way, for this example it is not a problem. For this example, as both are same, so it is not a problem. But which are not having the same number, so you will give wrong answer. So we have to collect the integer part in the same order, right? So try to remember this point. We'll see one more example, 0.8750. 0.875. So this is also having only the fractional part. So what we have to do? We have to multiply with 2. So 2 5s are 10, 2 sevens are 14, so 5, 2 eights are 16, so 7, so 1.750. So the fractional part now is 0.750, 0.750 into 2. If you multiply again with 2, so 2 zeros 0, 2 fives are 10 and 2 sevens are 14, so 1.50. Now the fractional point is zero point 0.5. So now if you multiply with 2, you will get 1.0. Now the fractional part is 0. So you can stop multiplying with 2. So again you collect the integer part in the same order. So in the same order, if we collect the answer for this given decimal number, the corresponding binary equivalent is 0.112. So this is the binary equivalent for the given decimal number 0.875. This is the binary equivalent. We'll see one more example. This example is an interesting one. It is not like earlier ones. So this is some tricky number. So those two examples, earlier two examples are one way. So this is another example, interesting example. So if we multiply the given fractional point 634 into 2, what we will get? 2 fours are 8, 2 threes are 6, right? 2 six are 12. So 1.268. So 0.268 if we multiply with 2, so 2 eights are 16, 2 eights are 16, 2 six are 12, so 3, 2 twos are 4, so 0.536. Now you take the fractional point 536 into 2, so 2 6 are 12, 2 6 are 12, 2 3s are 6, 7, 2 5s are 10. So 1.072. Now take the integer part 0.72 into 2. So 2 twos are 4, 2 sevens are 14. So 0.144 into 2. So it will give 2 fours are 8, 2 fours are 8, 2 ones are 2, 0.22288. Now if you take again the fractional part 0.288, again if you multiply, what you are getting? 2 eights are 16, 2 eights are 16, 17, 1. So 0.576. Now if you take again the fractional point 0.576, if you multiply with 2, 2 twos are 4, 2 2 6 are 12, 2 6 are 12, 2 sevens are 14, so 5, and 2 fives are 10, so 1.052. So for some fractional numbers, so we will never get the fractional part never, it will never become 0. So this process will continue like this. So this is the beautiness of this example. So for this type of problems, so it depends on whatever the problem statement mentioned in the exam. So in the exam they will mention, you give the answers up to some 4 points and 5 point or 5 digits. So for those you can take the answers up to those many numbers or digits and you can stop the answer. So for this example, for the given 0.634 decimal, the corresponding binary equivalent is 0.101001 and so on and so on. It will never end. The fractional part for this type of number will never end. So depending on the problem statement, you have to stop up. If it is mentioned you write up to 4 digits, you can write up to this and you can put dot dot dot. So this is the difference between the earlier example and this example. Is it clear for everyone? Is it clear or any doubt? So you can try these problems also on your own and give your answers in the comment section. We will provide the answers. You can cross check with the answers that are given or provided. So I request everyone to subscribe our Easy Tech channel and inform and share to your friends. So in this module, we have seen decimal to binary conversion and binary to decimal conversion. So in the next lecture, we will see what are octal numbers and what are hexadecimal numbers and their conversion to binary as well as vice versa. Thank you for watching.